Thank you, sir. Thank you. Um, okay, let's get started. Today, we will explore how remote sensing technique can help us understand and monitor the environmental pollution, especially water pollution. So, for the next 1 hour, we'll start how actually what water quality means, how it traditionally been measured, and then move slowly into how satellite data and other tools like Google Earth Engine and CDAS can support large scale monitoring and analysis. So, um, water quality affects life in so many ways, actually, by to the human health, aquatic system, drinking water, and recreation, etc. Traditionally, the agencies like US EPA set criteria for surface water quality based on health and environmental impact. When pollutants get into the river, um, a lake, or any other ocean, even any other water body, that can make the water unsafe for people and disrupt the entire food chain. So, when we talk about water quality, we are not just talking about whether the water looks clean. We are totally talking about measurable environmental and biological condition that affects the living system. So water quality can change because of natural processes, but human activity are typically the biggest drivers of it. Stormwater runoff can wash pollutants from streams. Agriculture fertilizers can add too many nutrients, leading to algal bloom. Changing land cover, like removing trees nearby the water body, can change the water temperature. Even large construction projects can alter the water flow and sedimentation processes. Understanding these influences is important because remote sensing can detect many of these changes at a regional and global scale as well. So, traditionally, water quality monitoring requires collecting physical samples. Researchers visit to the site and measure the things like chlorophyll, pH, temperature, clarity, turbidity, dissolved organic matter, sediments, bacteria, and etc. So these methods are accurate, but they are limited with the cost. The limitations are it is very expensive. It requires trained team, and you can only cover a small area. You may not, collect the data frequently also. So remote sensing complements all these limitations by expanding the coverage and giving us regular repeat monitoring. So why satellite? Satellite provides us the consistent observation over large area with regular revisiting times. This makes it easier to detect the changes over time, like algal bloom that appears within days. It changes daily. Almost uh, most modern air and observation missions provides the data for free only. So once you know how to work with the data, you can apply it globally. So we still need ground measurements for the accuracy and for the clarity of that to see whether the area or the water body is polluted or not in a particular year with a specific parameters. But satellite fills the gaps, especially when the manual sampling is very difficult or it is very costly. So water quality indicators visible to satellite actually. So different water quality properties affects how the water reflects sunlight. Satellite can measure this particular parameter and infer so many informations like chlorophyll A, cyanobacteria, suspended solids, water clarity, color, dissolved organic matter, even surface temperature and salinity as well, we can do. So this makes the satellite very powerful for studying the aquatic ecosystem at regional and global scale. So these are all the current satellites and sensor. Um, Several satellite missions are used for water quality monitoring, which has advantage in resolution, revisiting time, and spectral sensitivity as well. For example, Landsat 8 and 9 moderate spatial resolution. It has good. It is very good for medium-sized lakes or water body. Sentinel-2 high spatial resolution, and it has short revisiting time, excellent for inland waters. And MODIS and VIRS, it has coarse resolution but huge area coverage daily we can get. So often combining the satellite data gives a better result than relying just one. So we can for the best result we can use it in the combination for the comprehensive analysis. Because no single satellite is perfect, researchers often merge or fuse the data for the from multiple satellites, as already mentioned. For example, Sentinel has high spatial detail. Landsat provide a long historical period. Sentinel-3 provides MODIS and VIIRS gives frequent updates. So together, we can balance the spatial coverage, time resolution, and data availability as well. So here is a quick list of active missions. Some of these, like MODIS and Landsat, have been operating for decades. So that gives us long time series, which are extremely valuable for studying trends such as sedimentary load changes, increasing trend of algal blooms and temperature shifts. So each sensor, these are all the sensor bands. So each sensor capture light in specific wavelength band. So the presence of chlorophyll or dissolved matter changes the shape of the reflectance signature. So this is why certain bands, often in blue or green or red or near infrared, are used to derive the water quality parameters. So understanding these band positions allows us to choose the right satellite for a particular study according to our specified objective. So remote sensing for water quality. When satellite measures the Earth's surface, much of the light is reflected by the atmosphere. So before we estimate the water quality, we must correct the measurement to isolate only the water leaving reflectance. So this correction ensures our algorithm are based on the actual properties of the water, not haze or dust or even cloud. So let's see what are the inherent optical properties. Different material in the water absorbs and scatter light differently, actually. So sediment, for example, reflects strongly, while chlorophyll absorbs more blue light. So by analyzing the reflectance curve, scientists develop empirical model that allows us to convert the satellite reflectance into physical parameters like chlorophyll concentration or turbidity, etc. So workflow for water quality retrieval, the general process looks like first of all, getting the satellite reflectance, correct for atmosphere changes, compare with the in-situ data, and develop or apply the models like statistical model or machine learning for the advanced analysis, and validate it with independent measurements. So algorithm development is crucial because different lakes behave differently optically, or so one model doesn't fit for all the water bodies. So that's the main requirement for algorithm development. So to build a good model, we need field samples collected close in the time to satellite overpass, and we need seasonal coverage, multiple sites, Also, we need enough cloud-free satellite data and scenes, independent data for validation as well. So if you are building your own model for lake, the rule is simple. The more field data you have, more reliable your retrieval will be. So that's the main thing here. So image processing softwares for water quality parameters. Let's get into CDAS. CDAS is a NASA's main software for processing ocean color data. It allows the user to perform the atmospheric correction, data visualization, algorithm development, and even in-situ data acquisition. If you are processing Sentinel-3 or NASA Ocean mission, this is often a very best tool. So this gives fine control, but requires downloading data locally and install the process modules as well. Now let's get into Google Earth Engine. I missed the giving the overview of the Google Earth Engine platform yesterday, but we'll see a overall outline of this Google Earth Engine platform. So it takes actually different approach. Instead of downloading the data and processing it locally, you can analyze the massive data sets directly into the cloud. So no more worrying about disk space or computing power or nothing. So you just write a short script of it basically runs in JavaScript. So you just write a short script and GE process data on Google server itself. So GE API and examples, like with Google Earth Engine, we can load the satellite data like namely Sentinel, Landsat, MODIS, DEMS, digital elevation models, climate data sets, etc. And we can also run customized algorithms and export the result, and we can apply the machine learning techniques, and we can also build up apps and dashboards as well to publish the real-time monitoring of our data processings. And the coding can be done in JavaScript or in Python as well. Mostly people use JavaScript for in Google Earth Engine. The hands-on workflow is very fast, and it is very scalable and ideal for monitoring large number of lakes or water body, or mapping the changes over time, like temporal analysis, time series analysis. So, advantage of remote sensing. Remote sensing gives us so many advantages we can't get rid of, we can't get from the field surveyor alone, but it gives the long-term archival data, that is historical data, and wide synoptic coverage for the comprehensive analysis, and frequent revisiting for high temporal analysis, good spatial detail in mission like Sentinel-2 and other high resolution data, and it is completely free of cost. So this makes it possible to build automated early warning systems for blooms, sediment spikes, or even pollution events. But it has its own disadvantage as well. Satellite monitoring is not completely perfect. It has some limitation. Let's see one by one. Small ponds, maybe very too small for core sensors. For example, if a sensor has decent or low resolution, the small ponds cannot be absorbed through that sensor. And very shallow water causes bottom reflectance interference as well. So this is not the direct water reflectance. The sea bed is also influencing the reflectance pattern. So in shallow water area, that is also a problem in satellite remote sensing. Optical sensor cannot see through clouds. Only microwave sense radiant sensor can penetrate into the clouds, but optical cannot. And atmospheric correction is very much needed, and it is very challenging too. It has so many steps to do, that is coming under the pre-processing of the satellite imageries. And ground truthing is still needed. Ground truthing is very much needed for validating a particular study which has the usage of satellite remote sensing data. So remote sensing does not replace field work basically, but it makes the field work more efficient by adding it the holistic view that we can say. As I said before, atmospheric correction is very difficult. So let's have just a glance about it. Atmospheric correction is one of the most critical step. Up to 90% of the light measured by the satellite may come from the scattering in the atmosphere itself. So if we don't correct it, then it properly, then our water quality estimation will be completely wrong. So there are several models like 6S, um, Acolyte, and NASA BG, Hydrolytes, and each has its own strength and disadvantages, but still, these are all the existing model of atmospheric correction for water quality parameters. So this slides explains the chlorophyll model. Different algorithms exist for chlorophyll estimation actually. So for low chlorophyll water, color index based algorithm are used. For high chlorophyll waters, often eutrophic lakes, band ratio polynomial models works better. So the choice of the algorithm should be depend on the optical characteristics of that particular water body. Total suspended sediments and Secchi depth models. So these can be derived from the ratios of the specific spectral band. For example, red to NRA ratio for total suspended solids and blue to red edges ratio for clarity. Again, these relationship come from the strong statistical correlations between the reflectance and real field measurement. So these in situ data and the remote sensing data go hand in hand. Cautions in the model selection. One important takeaway, never blindly apply a model from the literature. Lake differ like dramatically, like every single parameters like turbidity, sediment type, or water color, even algal types, all influence the reflectance difference. So modern machine learning methods can help, but even then, good training data sets is very essential. And incentive data is also very much needed for an efficient, results. So yeah, I'm done with the presentation. Let's get into the practical session. Sure. Okay. So today, we are going to explore one, two, three, four, five, six different analysis. In that first, chlorophyll. Second one is turbidity, both of them from Sentinel data. And we are also going to establish the time series analysis of chlorophyll and time series analysis of turbidity. So fifth one is salinity time series analysis uh, for a water body. And finally, ocean pollution monitoring. It's a comprehensive study. It has four different uh, parameter growth we'll be seeing on that particular code. So altogether, the study area I've chosen for chlorophyll and turbidity study is Vembanad Lake system, which is existing in the famous coastal districts of Kerala, Ernakulam and Alapi. So that is for chlorophyll and turbidity. And for salinity time series analysis, I have taken the whole Kerala coast. And for pollution monitoring analysis, it's a comprehensive study I mentioned. No, so that particular study uncovers the whole uh, east part of Arabian Sea, which also includes the Kerala coast. Okay. So I'll just write a line by line code for you guys, just for one code, that is chlorophyll analysis. And then I will just run all the codes that I have already saved as scripts in my account, and we will try to visualize it one by one. So let's get started. Okay. Mhm. So this topic is lake water chlorophyll. Okay. Okay. First of all, we will just define the steady area by coordinates. Okay. Mm, for that, variable water body area equals show. So I have coordinates already with me. So I'm just gonna type it over here. Meanwhile, if you guys have any doubts or popping up with any, uh, you know, struck points, just let me know, unmute yourself and talk, or else just give it in the chat box. I'll tackle it in the end of the session. So these coordinates are for Vemana Lake system. plasma. Next step is center the map on our study area. So map dot center object. What is our variable name? Is water body area into the scale of 10. And also we are just adding that particular map. So add layer. What is that layer? Water body area. Open bracket, close bracket. On the name of study area. What is the study area name? Vembanad Lake. Okay, close bracket. Paste it positively. That's it. Now what we are going to do is define the time range. So it is up to um, starting of 2025. So the steady period is 2025. Okay. So again, variable. Sorry, 2025 0101. Okay. Where end date is present. So for that present, we are just giving the EE date, which is new date up to the date. We have to see end date. Now what we are going to do is load the internal date. So for that filtering process, variable sentinel collection is equal to VE dot collection. But we are just filtering the date from start year to end year, right? So that was the sorry, start year to end date, right? Start year to end date. Also, we are filtering the boundary. That is the function called filter bounds. So what what is our boundary actually to cut it over with this water body area, right? That's it. Also, we are just filtering the cloud percentage. Filter e dot filter dot cloudy pixel percentage, which can be 20. Okay, here apostrophe will be okay. It can be 20. Let's say 20. Okay. No, the dot function. Now these steps will used for selecting the band. What are all the particular bands we are going to establish? So here comes the role of satellite bands, especially here chlorophyll, right? Image dot select. We are selecting again, multiplying it with 0.0001 for converting the reflectance values. This is the formula for converting the reflectance value from the band of uh, Sentinel to variable NDWI means normalized difference water index. This is also a spectral indices. It's a simple map algebra of the pixel values. So this is a band involving third band, sorry, and 3 and band A. And we are naming it as NBWY, right? Right. And we are masking out the water areas from NDVI, okay? NDVI, just we are going to get 0.1 meters away from that buffer. Now, here comes the chlorophyll index. So, where chloro, that is called from water mass, okay? It's not written chlorophyll index. Sorry, where chlorophyll index is equal to, we haven't called the chlorophyll index itself. So, selected bands of band 5 and band 4. If not returned to chlorophyll index, we are just going to copy the properties of this image. Draw the start time, that is Jan 1st, 2025. To the system timing. Where is the open bracket? Yeah, we have opened the bracket for map function image now. So we are just closing over. Okay. Actually, we are naming this chlorophyll as NDCI. NDCI, normalized difference chlorophyll index. If this into symbol gives, it shows means it has some error. So let's just try to rectify here itself. Here it should come one comma. Mm. Here bracket has to be closed and then multiply it with 0.0001 and now close the bracket. Yes. Okay. Now next step. So let me just explain up to here so that you can have a clear idea about it. So we have just defined the steady area here by giving the coordinates. So this creates a polygon by using this coordinate lat and long. And the polynate here, the polygons are representing our steady area, which is our steady area, our Vembanad Lake. And this will be used to clip the image and reduces the loading time. So map center and map add layer. So it is to view the map or our particular layer, process layer in the center of the image, in center of the view. Also, the polygon added to the map will be, um, but it is like this true is for loading that particular map um, into the Google Earth Engine platform. That's it. So this January 2001 is our analyzation starting date, and up to today's date, that is 20th of November 2025, we are just going to run the script. And that is the end date. This var sentinel collection equal to ee dot image collection open bracket Copernicus slash s2 underscore sr underscore harmonized. It is the this particular code, this particular line loads the Sentinel-2 surface reflectance collection where the atmospheric effects have already been corrected. So S2 level, it is the corrected level data, so no need to worry. So all these filters, first one is to select only the images into the date range. And the second one is to select only the image covering our steady area. And third filter is for the cloud cover up to 20%. And now we are processing the data and we are processing the scale reflectance. So Sentinel-2 reflectance is stored as integer. So we have to multiply it with 0.0001 to convert it into uh, real reflectance values, that is real number 0, 1, etc. And then we have computed the NDVI for water mask. So NDVI actually highlights the water pixels and land pixel get masked out using NDVI less than zero point 0.1 value. And then comes NDCI, that is normalized difference chlorophyll index. The normalized difference chlorophyll index formula is band 5 minus band 4 divided by band 5 plus band 4. So it is used to estimate the chlorophyll concentration from Sentinel-2 data. And then we are applying the water mask in this step for our chlorophyll data. And time information is also being preserved in this copy properties line. And now let's just print the processed data. Print details of the filtered Sentinel data. First, printing the filtered Sentinel. Sorry. From Sentinel collection. We have printed it, and now we are just going to visualize the chlorophyll index for our string. Variable NDCI composite equals to Sentinel collection dot mean dot clip for water body area. Okay. Oh. Now what we are going to do is add the computer NDCI as a layer also on the map. Okay, for that map dot add layer. What is the layer? NDCI composite. Because we have named that layer as composite in the previous visualization, so we are just giving the name as NDVI composite, comma. What is the minimum? We are just going to assign the minimum maximum value. Minimum value as is 0.2 and maximum value is the minimum is 0 minus 0.2, maximum is 0.2. Where the palette we are assigning now color palette. Let's say blue. Sorry, we need to yellow and red. Typical colors. That's it. And now selecting the center to images. Image with a specific date range. Variable 2025 June, the first date and up to end date. Okay. And we are going to mean it. And we are going to clip it for water body area. Now what we are going to do is add that particular layer into the map. I mean that selected layer. Okay, for that map dot add layer. What is that name? Target image. Right? Here also we are going to assign the minimum maximum value, minimum as minus 0.2, maximum 0. Valid is the same. We are just going to copy paste this thing. Okay. Also, this is called NVCI. What is it? June to December. That's it. What is the error over here? We didn't close a bracket. Okay. Let's just run. So before running it, let me just explain the rest of the lines. So what we did is applying the filters. Um, sorry. Here we have printed the um, filtered Sentinel data, and then here we have just displayed the map by giving the maximum minimum value, and we are have given the color palette as blue represent low, yellow represent medium, and red represent high concentration of chlorophyll index. Mm, and then here, this date filter is like, what is the start date is 2022, uh, June month of first, right? And the clip is over the steady area, and we are performing the mean value, and we are just adding the same we are just adding the layer with the same visualizing parameter. Let's just run. There is some error showing chlorophyll index is not defined. Mm. So the steady area has been shown here. This is the Vembanad Lake system's boundary. The error shown here is chlorophyll index is not found, means this uh, chlorophyll index written somewhere the spelling mistake happened, or any comma or dot missed over here. Let's just try to fix out. Where
Hello, sir.
yes,
I think spelling for chlorophyll is CHLO. Is the mistake?
exactly. Mm. This was right, no? Color and
In line 48, there is another spelling issue.
Okay. NDCI composite.
47, sorry.
Okay. So basically, the lines with the double slash, I mean, the lines, those which are looking in green color. So that's all just comments for for our understanding. So it really doesn't mean it doesn't affect the code to run. So hectic. So yes, here chlorophyll index dot update mask. Okay, code run perfectly. Thank you guys. So yeah, the study area is being visualized over here, and this is NDCI for uh, um, the study area, which is mean up to 2025. This is for Jan 2025 to present, and this is for Jan to December 2025. This is also a mean calculation, and in some of the area the map is missing. That's because of the cloud presence. And here we can able to visualize because in Kerala mostly I've observed only in Jan, Feb, and March. These are all the three possible months where the cloud-free data is available for Kerala region. So I guess that would be a problem because we are just observing the chlorophyll after June. So obviously the cloud-free data is present on Jan to March. So the cloud cover is a problem for this particular layer. I hope you all understood what I've explained in this code. Let's just run the other scripts that I've saved for you guys. This is, uh, let's just save this. So this is chlorophyll time series analysis for our study area. This is also same story, but we are just going to visualize it with post monsoon and pre monsoon. We are just giving the post monsoon uh, layer separately and pre monsoon layer separately. All others are same. Let's just run. So this is just a basic uh, visual reference of water mask. This is NDCI for post monsoon 2024. This is for pre monsoon, that is January to May. Okay, this is our study area. It's taking time to load. Okay. And let's see turbidity. This is a steady area, and this is the club click turbidity index. And it's time series analysis. Okay. Uh, in turbidity, there is no much difference on this lake area, I guess. That's why it's showing the single bland color all over the steady area. There is no color difference. We can see some color difference over here, which have high turbidity. Otherwise, it's all same. Why it's showing high turbidity inside this inland water means obviously the land runoff and agriculture influences and uh, uh, urbanization, rapid urbanization also. So these are all the influencing parameters why the reason why it is showing the high values in inland waters than the uh, coastal area. So chlorophyll and turbidity, it's done, and its time series analysis also done. Now let's see for salinity. Salinity time series analysis, I have taken the entire Kerala coast as a steady area. So here, yes. So from 2001 to 2020, this is the salinity satellite observed salinity for the steady area. Sea surface salinity is the proper layer name of this. So we can observe the proper up and down trend. Now let's look at the final script. So it has four different parameters. One is particulate organic carbon, planktonic growth, chlorophyll concentration growth, and sea surface temperature growth. So all these parameters are very much important um, for the observation of water quality. So all these maps cannot be visually, you know, uh, giving visualized with different color palettes because since it's covering a very large area, it covering almost uh, east part of Arabian Sea. So we'll just look on the time series analysis. Okay, this is for so this is particulate organic carbon (POC) growth in Eastern Arabian Sea. Some of the area showing some of the time period showing very high range. And During that time itself, there is a sudden fall also. And here is the phytoplankton growth. Also, it is like it is I think northeast monsoon. And during northeast monsoon, the planktonic growth is very much high over here. The same chlorophyll content is also very high because chlorophyll is indirect indicator for phytoplankton presence. And sea surface temperature, it is a very ideal, like it is a gradual up and down. So this is covering the year for 2000 and 2001. So yeah, it is a complete 2 year channel observation for SST growth. And this is how we can able to have the continuous monitoring and real-time monitoring for water quality using satellite remote sensing. Any doubts, questions? Right.
Hello. Uh, do you have any doubts, participants? Hello. Do you have any doubts?
Hello, sir. Hello?
Yes. Yes,
Can you
Riju.
hear me?
Yes, we can hear you.
Yes, sir. Um, okay. Is it possible to monitor animal migration? Huge number of migrations like birds and animals through remote sensing.
Um, Actually, no, we can able to track the migration path. That may be possible, but real-time migration of birds and animals, it's I can't say it's impossible, but the real-time monitoring satellite and in the satellite is actually on the very much high altitude. For these lower level of observation, we need high-end lens sensors like surveillance camera, etc. for concentrate on a particular area to track the animal migration or birds migration. But we can actually track the possible ways through which the birds are tracing out from one particular area to another particular area by coordinating all the environmental analysis, environmental properties, temperature, and what is a possible um, possible environmental existence or for that particular species thrival on a particular area.
Okay, sir. We can detect metals. Is that possible? Because
What?
you tell me that a particulate matter carbon, you can detect the salinity, turbidity of the water quality. Is there
Okay.
we can detect metals like a lead, the particular metal?
No, 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 no. That's not possible. Those like that kind of that level of chemical and physical parameter analysis will be done by uh, those guys who are working in the lab collecting the samples. So that is impossible in satellite remote sensing. But it is possible in certain level by using the hyperspectral remote sensing, where we can identify the chemical composition difference between a water column and another water column. But uh, chemical components cannot be distinguished through satellite remote sensing. Yeah.
Oh, okay, sir. Sir, I am working in pollution control board as analyst, and now I am pursuing environmental science, sir. I have passionate to work in remote sensing. Is there any scope?
Okay.
And tell me, could you guide me, sir?
Of course, like I'm so happy that you have opened your GIS world. It is a very big scopeful domain where all the every each and every single domain is have the location based services, whether it is Amazon, Uber, any delivering delivery partner, or even all the academics and researchers have this location based analysis or geospatial based analysis, and not just analysis to just to exhibit their results spatially, to represent their numbers and values spatially. They need maps and analysis, analyst and GIS. So I guess it's a very much scopeful and fruitful domain. Of course, my guidance will be there. Like, contact me whenever you need it. Take my I'll share you my email ID on LinkedIn. You can contact me anytime.
Okay, sir. Thank you, sir. Sir, I don't know about that coding's basics and all.
Okay.
I have worked in AirDAS and ArcGIS, but I just
Okay.
upload the Landsat image and then
Mhm.
I see the vegetation and all. But
Mhm.
in Google Earth Engine, you'd have done codings and all. I doesn't know about that. That's why
Okay.
I'm asking. What course which is suitable to learn that, and how can I start that?
Okay. I recommend you to, if you really want to study or learn programming language, Python is an apt one, because Python language is the base language for all the algorithms that has been used for machine learning and artificial intelligence these days. If you want to learn a programming language, I would recommend you Python, obviously. But for Google Earth Engine, JavaScript is mostly used. But Python can also be used, but Python scripts are very less than JavaScripts. So I guess all the scripts that I have given for you is readily available in the catalog itself. You can explore the catalog tab in Google Earth Engine, or n number of scripts are available in the browser and GitHub platforms, etc. Even Google Earth Engine platform itself, it's producing, providing its own scripts where we can explore, just change the date range and give your coordinates of your study area, and specify your band that you need to extract from a particular sensor's band. That's it. You'll get the result. You will just need the visualization parameter, and you just need to have the knowledge of allotting the maximum minimum value of that particular parameter. That's it. So if you have that, it's very easy to work on Google Earth Engine. But if you really want to learn, to start learn programming language, Python is your go.
Okay, sir. Thank you, sir.
Thank you.
So is there any other queries from the students? Yeah, I think Felix is asked something. So maybe is it okay to combine data from different sensors when doing long-term series analysis, or will it not be comparable? So, Sharat?
Okay. Okay. Time series analysis is basically temporal analysis. Temporal to overcome this time lapse between each sensor, it is very different. We have MODIS data that is with high temporal resolution but low spatial resolution. But we have Sentinel data which has low temporal resolution but high spatial resolution. For overcoming the temporal resolution problem, we cannot combine MODIS and Sentinel. Whereas we can combine these two data for both spatially and temporally, where we can achieve the uh, temporal resolution problem by Sentinel and spatial resolution problem by Sentinel and temporal resolution problem by MODIS, because MODIS revisiting time is 1 day. Every day, the daily data is available from MODIS, but Sentinel is not the case. But Sentinel has high spatial resolution 10 by 10 meters. So we can combine these two sensors. Not in the Google Earth Engine. It cannot be used. Google Earth Engine cannot be the that efficient platform to combine the data from different sensors. But we can use Snap, or we can use CDAS. We can use ODV or NV, ERDAS, etc. for combining or fusion of two different data from two different sensors. I think I have answered Felix's question. Is there
Thank you.
anything more should I add? Okay, thank you.
Okay, I think there is no more questions from the participants today. So maybe we can wind up for today, and tomorrow will be the last day for this one. And at the end of the session, Sharat will share the slides. And also, if you have some doubts, you can ask it tomorrow as well. And he will share his contact, as he mentioned, tomorrow at the end of the sessions. Okay, thank you so much, and good night. Good night. Okay, thank you, Sharat. Thank you so much. Thank you.